Chapter 12, Number 20. At some point along the direct path from the center of the Earth to the center of the Moon, the gravitational force of attraction on a spacecraft from the Moon becomes greater than the force from the Earth. A. How far from the center of the Earth does this occur? At this location, in B, how far is the spacecraft from the surface of the Moon, and how far is it from the surface of the Earth? So this is the point that marks the boundary between sort of near Earth and near Moon space, and so we should draw a picture of what's going on. So we have the Earth and the Moon and the spacecraft between them. My intuition is we'll probably have to be pretty close to the Moon because the Earth is so much larger in mass. And then we need to make some definitions of what is going on, what our variables are going to be. So here we have the mass of the Earth and mass of the Moon. And m is just the mass of the spaceship. And then we say the well-known astronomical distance between the center of the Earth and the center of the Moon, a number that I will look up probably on Google, is d, and the distance at this moment of the spaceship from the center of the Earth is x. And then that means by continuity that the distance from the Moon to the center of the Moon to the spaceship is d minus x, which is that one. And our key bit is, if we're talking about the moment that the attraction to the Moon becomes more than the attraction from the Earth, then really at this moment they should be equal. So we should end up with something like Fg due to the Earth equals Fg due to the Moon, at least in magnitude. I'm not worried too much about their direction here. And so we have something like g of the mass of the Earth times mass of the satellite over x squared is g times mass of the Moon times mass of the spaceship over d minus x squared. And we can see right away that some things go away. Universal constant g cancels out. This is actually why it was hard to measure g. It always seems to cancel out in things. And then the mass of the spaceship itself cancels out, which is why they didn't bother giving it to us. And so we're left with a somewhat simpler form, which is that the mass of the Earth over x squared is the mass of the Moon over d minus x squared. And I should probably get some values for these things, so I'm going to go online and get the values of the mass of the Earth, the mass of the Moon, and so on. So I just used some basic Googling, but this stuff's also in the back of your textbook and is all over. Everyone knows where these are well-known values, at least as of the Apollo program. So we have the mass of the Earth is blah, the mass of the Moon is blah, and the distance to the Moon is 384 million meters. On the one hand, this would be a solution of what is basically just a quadratic equation. On the other hand, the numbers are annoying, and so there are some tricks that make the solution somewhat more direct. We're going to make two auxiliary definitions. These are just for algebraic manipulation. They have no real physical import, but I'm going to say let's find the fraction of the distance that the 0 point is of the total distance to the center of the Moon, and I'm going to call that f, which will be some number I can find. And then along the same lines, I'm going to take the mass of the Moon and divide it by the mass of the Earth and call that k, which again is just some constant, the ratio of the masses. This is just going to clean up the algebra for us. This is kind of now just a math game rather than any real physics thing. But this does allow us to make some substitutions. So we can go over here and we can say that the mass of the Earth, and then notice that this is the same as saying that x is f times d. So over here I'll have fd squared. And then I'll have the mass of the Moon, but the mass of the Moon I'll be able to say the same way. The mass of the Moon is k times the mass of the Earth. So I'll call this just k mass of the Earth over d minus, and again replace x with this thing, which seems to be a step backwards. We seem to have made the problem way more complicated, but some nice things are going to start happening. For example, the ME's will now go away entirely, so that huge number is not coming around, and MM has gone away. So we're not getting ratio of weird huge numbers. This leaves us with 1 over, and I'm going to replace this now with f squared d squared, which is what that turns out to be. And over here I'm gonna still have k, and on the bottom I'm gonna have d minus fd quantity squared. And I'm going to pursue that a little bit more, and I'll say, oh, that's k over, and here I can pull the d out, so I have d squared times 1 minus f quantity squared. And now I can see as well that the d's are going to cancel, and I'll be left with 1 over f squared equals k over 1 minus f quantity squared, which is the same equation, but going to be a little bit easier to manipulate. And from here out, we just do some basic algebra. So I cross multiply, and I get 1 minus f quantity squared over here equals k times f squared. And then I square the left-hand side, and I get 1 minus 2f plus f squared equals kf squared. And then bring everybody to one side, and I'll have k times f squared plus 2f minus 1, minus 1 minus f squared is 0, or k minus 1 quantity f squared plus 2f minus 1 equals 0. Which is just a quadratic. So we can use a quadratic equation solver, or we can solve it by hand using the infamous, x equals minus b plus or minus square root of b squared minus 4ac, and then all of that over 2a, where we have identified things like this is the a, and this is b, and this is c. One way or the other, we have to basically just do some silly algebra, and we get a number. For example, I went online and found a site called Math is Fun, which has a built-in quadratic equation solver, and threw in R values where k is roughly 1%, and therefore k minus 1 is the thing that's shown over here. And when you do that, we get two answers, which is actually not that surprising, but only this one makes sense because we need x to be less than d because it's between the Earth and the Moon. So we find that x over d is 0.8998, which implies that x is 3.46 times 10 to the 8 meters. Part B is additionally a little bit annoying because they want to know the distance to the surfaces. This is the distance to the center. So the first thing is, for the distance to the Earth's center, we would say, surface, we would just subtract the Earth radius from this. So what we want is what we might call height above the Earth, which is going to be x minus the radius of the Earth, which is going to be really basically the same thing, because the radius of the Earth is like 6 million meters, and this is 346 million meters. So we get something like 3.39 times 10 to the 8 meters, which is incomprehensibly large. And then likewise, the height above the surface of the Moon would be d minus x minus the radius of the Moon, and that turns out to be 3.73 times 10 to the 7 meters above the Moon. So those numbers end up not being all that interesting. Actually, the 0.89 is more interesting. The fact that you go 90% of the way to the Moon before they balance, which tells you that the Earth's mass plays a much bigger role because it's about 100 times larger.